Alright, still in section 10.2. We're now ready for example 2. Example 2 wants us to compare and contrast the behavior of these two functions, a sub n and b sub n. A sub n is n to the 3/2 over n to the 3/2 plus 1. B sub n is -1 to the n, which makes it alternate, n to the 3/2. Oh, and that's the only difference. Alright, so if I started plotting dots, so the first thing I can do on number 1 is I could take, or part A, is I could take the limit. If I take the limit as n goes to infinity of a sub n, the powers are the same, the answer is going to be 1. But here the limit as n goes to infinity has a problem because it's going to keep alternating. Now, it's still going to approach 1 if I'm putting in n is even, but it's going to be approaching -1 if I'm putting in n is odd. So this one, we have to say this one diverges. Because what happens when you graph this guy, if you start plotting your dots, 1, 2, 3, 4, and putting them in there, 1 would be up here, and your dots would appear going like this. I'm not plotting them, I'm just identifying what happens. And if you do the same thing on this one, you have this back and forth thing going on. You have, let's put 1 in the same place. And the first one goes about here, and the next one's here, and the next one's here. Oops, going the wrong way. This one's going to be here, this one's going to be here, and what's happening is they are both getting closer and closer to a boundary. This one as well, only it's every other term that does it. So they're bouncing back and forth. If they're bouncing back and forth, we have to say it diverges. Even though we can see that they are going somewhere, they're just not going to the same place. So that little -1 to the n there alters the whole problem. So that's what I wanted to know. Example 3, graph the following sequences and discuss their behavior. Part A says 0.75 to the n. So if I look at that and start plotting numbers, 0.75 to the 1 is 0.75. 0.75 to the 2 is going to be smaller than that, and I don't have my calculator handy. Hang on one second. Okay, so as I graph these, I'm just going to do a really rough graph. Here's 0.75. When n is 1, I was there. When n is 2, I was lower. And then it keeps getting lower. Whoops, that dot's a little off. And so on, dot, dot, dot. So what can I say about this one? It decreases to 0. So it converges what's known as monotonically to 0. And if you say something is decreasing monotonically, it is in your textbook. But if it's only decreasing or only increasing or only non-increasing or non-decreasing, then it's considered monotonic. It only does one thing. Okay, so part B, we're doing the same exact question, only it's going to alternate. So if I'm graphing that one, it's going to be a little weird. The first one, again, is at 0.75. Actually, the first one will be -0.75. And so, there we go. The first one will end up being here. The next one's going to come up here. And then it's just going to start going. I'm not going to put dot anymore, but it's going to start going like this. And then this one over here. And then this one, and then this one, and then this one. And they're going to get closer and closer to the x-axis from opposite sides. So while it decreases to 0 as n increases, so it's oscillating, but it does converge to 0. because they're both sides are going to the same place. And it's not monotonic because it is doing it from opposite sides, back and forth, back and forth, back and forth. Okay, part C wants us to look at 1.15 to the n. Now 1.15 to the n, if you start raising the powers on that, the number is going to just get bigger and bigger and bigger. So when you start out at 1, it's going to be at 1.15. I'll just call this 1.15. But the next one's going to get a little higher and a little higher and a little higher and a little higher. So this guy is increasing without bound, and so this diverges monotonically. And then part D, same thing, only with the alternating piece of it, 1.15 to the n. And if I graph that one, the very first one's going to be a negative 1.15, so down here somewhere. The next one's going to be larger than that, and then larger than that, and then larger than that, and then larger. And so these dots are increasing on the above the x-axis, but they are decreasing below the x-axis. And so this one is also blowing up without bound, and we're just going to say it oscillates and it diverges. So just because it oscillates does not mean it automatically diverges, because in example B it oscillates, but it does converge. They go into something. However, in D, they're going different directions. So that's number 3. Okay, this next example uses what's called the squeeze theorem or the sandwich theorem, depending on the textbook you're in. And the squeeze theorem basically says if you've got a function that you can identify another function that's always above it, and you can identify a third function that's always below it, and the two functions are heading to the same place, since the original function has to be in between them, it has to go there too. So, example 4 wants us to find the limit of b sub n is equal to cosine of n over n squared plus 1. So we're going to start out with the cosine of n. And I can make a statement about this. It is always between negative 1 and 1. So if I divide all three sides by the n squared plus 1, and since n has to be a positive number, this is not going to mess this up, because I don't have to flip my inequalities. Cosine of n over n squared plus 1 is still going to be between those. But now if I just look at that first one, we'll call this guy a sub n, we'll call the one we're talking about b sub n, and the third one c sub n. If I take the limit of a sub n, the limit as n goes to infinity of negative 1 over n squared plus 1, the bottom is going to blow up, and so this is going to go to 0. It's going to alternate back and forth, but it's going to head towards 0. And then if I go to, no, it's always going to be negative. If I go to the limit of c sub n, it's going to be the same thing, only all of its answers are going to be positive, but they're all going to be heading towards 0. The more n's, the higher the n gets, the closer it gets to 0. Now, since the cosine of n over n squared plus 1 is always between those two, we can say therefore, 3 dots mean therefore, cosine of n over n squared plus 1, actually I need to say the limit of it, and I left it out. The limit as n goes to infinity of that heads to 0 by the squeeze theorem. And that's number 4.